Last time we have discussed several aspects of writing a classical simple finite element program. We will finish these considerations today by having some thoughts about bandwidth reduction, and then we should be able really to write step by step admittedly simple but complete finite element program for an linear elliptic boundary value problem. This we will do, as I said, in the exercises step by step, and we should have finished that after Christmas. Okay, so what have we seen is that we have seen how to put up the matrix. We have seen the assembly process, typically element-wise oriented. And we have discussed now how to solve the emerging sets of linear equations. We have remembered what we know about direct solvers. Later on we will discuss a little bit more in detail iterative solvers and more advanced methods. But we have seen for using direct solvers under the assumption that no pivoting is necessary in the Gaussian or in the Cholesky process, then it's decisive concerning the operation count that we have a small bandwidth or that we have a small hull, a small profile. If we look at the Cholesky method, we know if the overall dimension is capital M cross capital M, and we have a bandwidth of small m, we need small m squared times m operations. And if you remember the simple situation of the 5-point stencil on the square, then if we take a row-wise or a column-wise numbering, then basically the small m is the square root of capital M, so we have already gained one order in complexity, only by this simple measure. But in the next simple step, if the domain is, say, a rectangle, then it makes a difference whether we take a row-wise or a column-wise ordering. And if it's either the domain is more complicated or our discretization is more complicated in the sense that we are now in the finite element setting, we have an unstructured mesh, then of course the general question arises what to do. How shall we number the degrees of freedom? How shall we number the nodes in the interior plus eventually those at the boundary such that we have a minimal or not too large bandwidth, not too large hull or profile? Okay, I will discuss a few methods in this direction. It's basically one method, and what is typical is that all these methods are more or less heuristics. It's not so easy really to prove something rigorous about it. So first let us again note how where those quantities come from to set up the data structure either as a band data structure or a data structure as an oriented list. If we want to store the hull, we need quantities like the bandwidth, or more precise, we need something like what we have called the row-wise left-handed bandwidth, and is correspondingly related to that this quantity FIA, which for the corresponding row denotes the first position where the first non-zero entry appears. Okay, yeah. Of course, up till now we said, okay, yeah, we get this structure by looking at the matrix. But of course, it's not a good idea to build up the matrix, store it in a two-dimensional entity, and then extract another storage possibility out of that. That should be all work in one step. And therefore, we just have to remind ourselves that here in the special case where we are with the specific finite elements, which we later on will call Lagrangian elements, or finite elements where the degrees of freedom are situated at the nodes of the element. This applies also to other geometrical shapes, not only to triangles and not only to 2D, we have the situation that where is it? It's not written up here. It's missing here on the transparency, unfortunately. Sorry for that. We know that we have that we have possible entries if we look at a row only for the neighborhoods in this triangle or for the neighborhoods in these elements in this framework I just sketched. So we just have to, we can define these quantities, for example, the FIA in terms of the neighboring elements in the corresponding triangles. So we only need the geometric information. We don't have to build up the whole matrix to see what is the storage pattern. We only need this geometrical information to build up these numbers FIA and MIA. They're basically the same. The one is I minus the other. And of course, then if we want to do so and want to restrict ourselves to a banded structure, also the bandwidth. And by this we can then set up our specific data structure and fill this data structure according to its indexing in the assembly process as we have discussed it. Okay, so now to this basic problem, how to number the nodes to make this structure as small as possible. The first thing is that we attribute a graph. We have our triangulation basically consisting of capital M degrees of freedom with the corresponding basis functions here. And we attribute to this triangulation a graph. I would hope that everybody has some notion what a graph is. So a graph is a discrete structure consisting of nodes, of vertices, which are connected by edges. And we only look at here at non-directed graphs. Or do we? Yes, it's non-directed. So what we do as the nodes of the graph, we take exactly the nodes of our triangulation. So for example, here we have an example of the triangulation we know already, consisting of triangles with the degrees of freedom in the edges of the triangles. So we just take those nodes here. So we copy these nodes here. And then we connect, then if we are in a situation that there is, we consider two nodes and ask ourselves, shall we connect those nodes with an edge in the graph? And this we do exactly in the situation where if there is a triangle such that the corresponding basis functions do not vanish on this triangle. And in our Lagrangian situation here with degrees of only function values as degrees of freedom, we have seen already that this applies exactly if there are neighbors in the corresponding geometric element here. So this means we just have to connect here the nodes of this triangle and of this triangle and of this, and so we get in this case exactly the triangulation again as the graph. This is not necessarily so. If we look at this example, this is now an example we will discuss later, consisting of rectangles or parallelipeds, where we have degrees of freedom in each of the 4 vertices here. And you see, we copy those vertices here. And now we connect all which are in the same element. But of course, also this and this are in the same element. So we have to connect them. So now here, the corresponding graph looks a little bit different than the underlying triangulation. So it's this graph, well, this is this information what we want to have. So what we want to have is so these are the candidates which can produce entries in the corresponding, say, ith row. If I look at the ith row of the matrix, of the stiffness matrix, the J's which have exactly this property, they for one triangle, they are the candidates. We might be lucky that an entry from one element is then cancelled by an entry from another element, as we have seen in connection with the Friedrich-Scalar triangulation, where we had first 7 candidates where non-zero entries could appear, but the element-wise entries cancelled, and we came back to our 5-point stencil. But this is a more crude condition at which we look here. Okay, so, and of course what we want to do is, if we have this index I, we want the possible indices j, which we have to consider, as close to the I as possible, to reduce the bandwidth and to reduce the profile. But of course this may then cause conflicts with numbering requirements, seeing the situation from other nodes. So what we are doing is the following, and that is what the algorithm of Cattell-McKee does. So we look at this graph that we just defined, and we call 2 nodes be neighbored if there is an edge connecting the corresponding nodes in the graph. So this is very close to the neighboring relations we had up till now. Then we define the degree of a node. The degree of a node is the number of neighbors which a node has. Okay, so those, of course, which have a high degree, they are in particular critical because they need a lot of spreading to cover all their neighboring indices, even in the best possible way. Okay, so the algorithm is the following. It's an iterative algorithm with, in the end, finite a number of steps working through this graph, in the sense that we first select one node to be the starting node. This node gets the number 1. This is the level 1 of the whole procedure. The level k of the procedure, after we have performed the levels up to k minus 1, is the following. If we have numbered already all nodes, of course we stop. If there are some nodes left, then we look at the level k of numberings which we have defined up till now. As I said, at the first level we start just with one node, and then we define the level k plus 1 just by taking all nodes which are neighbored nodes to the level k minus 1, but have not yet numbered up till now. Können Sie mal die Tür zumachen? Ist zwar schön der Gesang, aber doch vielleicht. Okay, so within each level we still have some degree of freedom how we number there, and one possibility, we can number also within the levels according to the degree, beginning with a node of the smallest degree. Okay, yeah, it's a very simple procedure, and I think the only way to see that it's of some use is to apply it several times after having it implemented. And then there's a further version, which is a very slight extension of this one, but may have enormous consequences in using it, the so-called reversed algorithm of Cattell-McKee, the reverse Cattell-McKee. And the only thing what happens is we first apply Cattell-McKee, we get some numbering, and then we put this numbering upside down. So we start with the last node and end with the first. For the matrix, this means that the matrix is reflected, or the sparsity pattern is reflected at this diagonal here. So not at the standard diagonal, but at the, don't know how this is called in English, at the opposite diagonal. And you see, for example, with this, look at this example. This is an example, and this is quite typical, of course, and that is something which one does not like at all. We have here our profile, but we have here the hull, but nevertheless within the hull we have large patches of zeros here. And but now we do this reflection, and out of the sudden these zeros are now out of the hull. So the profile here is much smaller than the profile here. This can be only seen in the hull. It cannot be seen in the band structure. The band structure remains the same. The band structure here is very disappointing. The band structure is here the full matrix, because we have an entry here and we have an entry here. There's no chance to reduce the band. And of course we have the same situation here and here. But in the hull, we gain quite a bit here compared to these parts. Okay, what can we tell about this algorithm? Not so much. As I said, these are two pretty simple estimates which indicate what is the bandwidth which comes out of the Cattell-McGee ordering. So first of all, there's a lower bound, so that is what is maximally possible, and it refers here to the capital D, that is the maximal degree of a node, and it refers to an auxiliary number I, which is 0 if D is even, and which is 1 if D is odd. And it says the bandwidth has to be at least this number here. So either D plus 1/2 in the case of an odd D, or D half in the case of an even D. And why is that? I think this is easy to see. If you only look at this special degree and don't exclude the possibility that further conflicts appear from other degrees, the only thing what we could do is for this degree with maximum, for this node with maximal degree, to do an optimal ordering for all its neighbors. And this, of course, means we put the neighbors immediately aside. And we have a left side, lower numbers, and a right side, bigger numbers. So in the even case, we just put half to the left and half to the right. And in the odd case, okay, we have to put one node to one of the sides. And so this is a number we cannot be better than this one. Okay, and what is the rest? So this is something which depends on the graph, and depends, and by this depends on the triangulation. It has not so much to do, and has nothing to do with the numbering. The upper bound has to do with the numbering, because it refers to the levels which are produced of the numbering. So this number capital Nk is the amount of nodes at level k. And now what is assume we have done this subdivision in these levels. That is a consequence of the algorithm, how the subdivision is. Assume we have this subdivision. So what is then the situation? So the worst situation which then can happen is that a node which is on level k minus 1 and which is numbered very, very early, say as the first node of level k minus 1, is in neighborhood relation to a node on level k, which is numbered very late, that is at the last position. So we just have to see what is the distance between these two positions, and this is just this number here. Nk plus Nk minus 1 minus 1. And then we have to go through all the possible levels and take the maximum of this. But this estimate also gives a little bit of indication how maybe how we can improve things. And there is a bunch of, so here are exactly what I just said here, and there's a bunch of heuristics. These are pretty old. I guess a lot of new also exist, and there are a lot of new algorithms with other heuristics. As it is here, okay, so what can we do? What we could do, we could say, okay, the starting node, these should be chosen at some edge of the graph, at the end of the graph. What does that mean? So we could either say, we take a starting node with a minimal degree. It's sort of exposed. It has only a few neighbors somewhere at the fringe of the graph. Or we just say, okay, it doesn't matter. It's only a few seconds that this algorithm will need. We just work through all the possibilities. We try all nodes as starting node and just see what comes out, what is the best possibility. The complexity of the whole graph as we go linearly through the nodes is just O of m tilde. M tilde is the amount of edges. And so if we do this full version, we have capital O of m being the amount of vertices times m tilde. So this is still something which is not so big. Okay, then a little bit related to the reversed version. Of course, one can work through the algorithm. Then this will give us a last node, the one which is numerated as at the last position, and then we take this node again as a starting node. That is also heuristics which work quite well. Okay, so we have now some basic tools to do this finite element implementation, and now we will change gears again. And now, after this introductory chapters, which we now had, we really start. That is, we define not an extremely general, but a little bit general problem, and the program which we have seen for our model problem, that is for the Poisson equation with the Dirichlet boundary condition, we go through this program for this more general equation. So that means we have first to set up the weak formulation. We have to check whether the conditions which were necessary in terms of continuity, in particular V ellipticity, are fulfilled, under which conditions. So the conditions on the coefficients will appear. Till now we had no coefficients. There were 1 and 0. And then for this, the next step will then be for this to do finite element discretization for this general problem, not only on triangles, but on general classes of geometric elements, not only in 2D, but also in 3D, and not only with a linear ansatz, but with a general polynomial ansatz. And of course, we need a rigorous analysis of all these things, because we only, concerning the analysis, we only scratched the surface till now. We have seen Sear's lemma telling us what we have to do is we have to estimate the approximation error of the space. But this we have not really done till now. We said, okay, it works. There is the interpolation operator which attributes an element which has a distance of in the order of small h under certain assumptions where we were still vague with these assumptions. So this will be the program for the next weeks, I think. And we start now. Before we can start this, we need to know a little bit more about Sobolev spaces. So this is not to substitute a function analysis course, or it would be even, I think, nice to have a course on Sobolev spaces where you can do all the proofs. I can do none of the proof. I can only indicate a little bit what has to be done. So let us remind the situation we have. In the simple situation of our Poisson equation, we have seen we have two equivalent formulations. the minimization formulation and the variational equation. And question was, is there a chance to show the existence of a solution in either of these two situations? Uniqueness is no problem. As we have seen, this comes from the definiteness. But is there a solution? Otherwise, if there's no solution, maybe we are approximating a phantom. But on the other hand, if we know there is a solution and we have a proper approximation theory, then we are able to compute this very abstract object up to arbitrary accuracy. That is the fascinating thing. Okay, so let's look at the minimization situation, and let's see whether we can sketch a proof how one could show that there is a minimum. Okay, so what we have, our functional has a quadratic part, and it has a linear part. I think it's hopefully clear to everyone how this looks like. It says 1/2 a of uu minus b of u. This a of uu, this is v elliptic. So in the one-dimensional setting, that would mean we're in the situation of a parabola, okay. But there are parabolas which have a minimum, and there are ones which have no minimum. Hopefully, fortunately, we are here in the situation because of this definiteness of the parabola which is open to the top, and therefore we are here in the situation of a minimum. So because of this situation, the first thing we can see is that this functional is bounded from below. So the quadratic term always wins compared to the linear term. So we have a finite infimum. The question is this infimum attained? Is there a minimum? And you know, in the situation where there is a minimum, there's always a minimal sequence. That is just the definition of the minimum. Minimal sequence meaning there's a sequence Vn in our basic space V such that the functional values f of Vn converge to the infimum. That is just comes directly from the notion of the infimum as the optimal lower bound, as the maximal possible lower bound. Now, the next step is not only to see a convergence of the functional values, but to see a convergence of the sequence itself. As we have, for a general f, this is problematic. But in our case, with this quadratic structure, we can conclude that the sequence Vn is a Cauchy sequence. Now it becomes decisive what kind of space we have. If we have the first definition of the space, which we try to put down a proper definition with these piecewise existing derivatives and so on, we cannot say anything anymore because we don't know, or we are sure that there are Cauchy sequences which do not converge in this space. If our basic space is complete, as it is with the H1 of omega space, as it is in general with the Sobolev spaces, then we can continue and say, okay, this Cauchy sequence has a limit. We call this limit V. The functional capital V is continuous. If the Vn converges to V, then also the f of Vn converges to f of V. But they also converge to the infimum. That means we have found an element of the space which attains the infimum. This is then the uniqueness proof coarsely sketched. So the continuity is a very important thing to know. So this gives us rise to the following assumption. So we have some vector space with a scalar product. In our example, the scalar product was either with the homogeneous boundary conditions, this A scalar product, or in the general case, what we have called the H1 scalar product, so having the derivatives and having the functions in the L2 norm. We have the scalar product, we have the induced norm, and we assume that with relation to this norm, the space is complete. So we work in a Hilbert space. Then we have our bilinear form, and from now on we do not assume anymore that this bilinear form is symmetric. We will later on see if we want to include convective parts in the model, in the PDE. Then the bilinear form becomes non-symmetric because we have a directed process then in the problem. And that is the point now where the variational equation formulation and the minimization formulations, they break apart. There is no minimization formulation anymore for this type of problem, but the variational equation formulation, this still exists. And on the discrete level, this means that we can still do Galerkin method, but there's nothing where we can do Ritz method. So from now on, we will concentrate on the more general situation, variational equation, Galerkin method. Okay, and then we have a right-hand side B, a linear form, and let's see what kind of assumptions we need. And we have seen already, we have formulated already a few assumptions, and actually these assumptions are assumptions which we needed to analyze the finite element method. And it turns out exactly those assumptions are necessary to prove the existence, and in this case then the unique existence of a solution. And what were the assumptions? The one thing was the continuity of the form. That means the bilinear form in modulus can be estimated by some constant m times the norm of u times the norm of v. Then the v ellipticity, the quadratic part AUU can be estimated from below by some positive constant alpha times norm of u squared. And then we need for the right-hand side, we also need the continuity, not only that it's a linear form, that is here in this case the boundedness, that is b of u, the modulus of b of u can be estimated by some positive constant times norm of u. And the best of these positive constants is then the operator norm of b. Okay, so this will be the assumptions under which we want to work, and we have seen already also for the later the coming analysis of the finite element method, we need those assumptions, and under those assumptions, and this is now the statement of the lemma of Lax-Milgram, and it's not really very hard to prove. Also, it has a name, therefore we will do it as an exercise. Is the variational equation, so the problem finds some u tilde in the space V such that A u tilde V equals BV for all V from capital V has one and only one solution. And none of these assumptions which are mentioned before can in general be omitted. Okay. So now let's see, let's go to the first step. The first step is the definition of the spaces, and we have seen the basic example of the H1 of omega we have seen already. So how is this? If we would take the A norm, let's go back to our Dirichlet, our Poisson case with the Dirichlet boundary condition. If we would take the A norm, then by definition, the two assumptions are satisfied with m equals alpha equals 1. But then we still have to distinguish. In our old definition, we have a non-complete space, so this will not work. So we need our new definition based on the notion of the weak derivative. And then we are at least in a situation which seems to work. We then have a complete space. We have not yet really seen that this is complete. I will make some comments on that. And we have then our assumptions fulfilled. The problem is not so much the norm, but so to speak, the elements in the space. It's not that we could save our space with the piecewise defined derivatives by taking another norm. If this would be possible, if we would have another norm in which those assumptions of continuity and V-ellipticity are fulfilled, then we have seen already that necessarily this norm is equivalent to the A norm. But in the A norm, we don't have completeness. So we also cannot have completeness in any equivalent norm. So the problem is not the definition of the norm. This is quite okay. The problem is that the space we had does not contain enough elements. And of course, there are functional analytic techniques in saying that every space has a completion of its space. But of course, we don't want to have some very abstract members of this space we really want to put our hands on. And therefore, we have introduced this notion of weak derivatives. So let me remind how this will look in general. We have introduced already here the space H1 of omega, and now we do this in general. So the general setting is that we have a bounded domain in Rd called omega, and we define the Sobolev space Hk of omega in the following sense. We collect in a set all functions, which then turn out to be measurable functions. So we have to deal actually with equivalence classes, as we have discussed it already. So we take all functions which are in L2 and which have the additional, so this would be the situation omega H0, that would be the original L2. And then in the general case for k equals 1, 2, and so on, we additionally require that this function has weak derivatives up to the order alpha, length of alpha less or equal than k, and these weak derivatives are supposed to be in L2. Okay. First, this is just a set of functions, and on this set of functions we now can introduce a scalar product. And what do we have? So we have the functions itself, and we have all their derivatives in the weak sense for derivatives of order up to k, and all those functions are L2 functions. If I multiply two L2 functions, then the result is integrable. Of course, this is something which has to be checked and which is the basis then for the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality is the proof. Depends how you would like to see that. So all these integrals which I've written here make sense. And I not only take one of them, I take all and I sum over those. I can have the sum either in the integral or I can have it outside of the integral. Of course, this doesn't matter. And the first assertion is what I've done here. I have defined a scalar product on this space. So bilinearity of this form, I think, is clear. Also, the weak, all the rules we know about derivatives, so all apply also to weak derivatives. Because weak derivatives is nothing but putting the derivative over to the test function. So if you can apply the rule at the side of the test function, you can also apply it for the weak derivative. So of course, also the derivative of a sum is the sum of the derivatives. You have something like the product rule, and so on. Okay. So we have bilinearity by this remark. We have symmetry. And the question is now about definiteness. Definiteness, I think, becomes clearer if we now look at the induced norm, because we have to check that it's really a norm and not only a semi-norm. We really have to check that the norm is positive if the element is non-zero. So let's look at the potential norm. So we set v equals to w here, and we take the square root of this. So from these inner, so in the inner, that's not denoted by some special sign. Of course, these are vectors here. That I'm not saying something wrong. No, this is just number. So this is then just the modulus squared of what we could also do this with vectors, and then would this be here the Euclidean norm. Okay, so we get then here the corresponding sum in or outside of the integral and the square root of this. And we can also rewrite this a little bit in this just by looking at this term and saying, oh, this is nothing but the L2 norm squared of the corresponding derivative. And from this we immediately see the definiteness both of the norm and of the scalar product, because of this, if this term vanishes, then each of the attendant, each of the summons has to vanish. Then of course also the L2 norm has to vanish, and we know already that the L2 norm is a norm. So this is the knowledge on which we build. We know everything about the L2 space. We know this is a scalar product. It is a norm. The L2 space is complete. And this knowledge we now transfer to the Sobolev spaces. So we have a scalar product. We have an induced norm. Okay. So one could do it a little bit more general, but in general I try to avoid to do so. What we have done here in the definition of the norm with a 2, we could have also done with a p. So instead of the L2 norm, we just take a p norm from the LP space. The difference then is that it's then only a normed space and not a space with a scalar product. There's no corresponding scalar product which induces this norm. So this is not a Hilbert space then anymore. In the end, it's just a Banach space. That makes it a little bit more difficult to handle these spaces. So therefore, I try to avoid this, but it gives a little bit more flexibility. And we will see in a second where this flexibility may be helpful. So if we would do so, we would then add up with spaces which have the name, or this is a standard notation, they are called W, K, P of omega. Why? Don't ask me why W and why H. This comes historically from two different schools, two different ways to introduce these spaces. And in one version, their spaces were called H. In another version, they were called W. Of course, this gave then later on rise to a very nice and historical paper with a title. Now you can guess what the title is of this paper. H equals W, of course. Okay, so this is historical notation, but this is standard notation here. The K from the order of derivatives and the P from the LP. So in this sense, the WK2 are our HK spaces. That's one point. Of course, there's one thing which is of not real importance, is the following. So what is the situation? Maybe we can see it best here. So what we have is we have certain derivatives. From those derivatives, we have norms. Here in this case, L2 norms. And now this gives a vector of numbers. And with this vector of numbers, we put together somehow to get, again, a number which is then supposed to be the norm of the quantity we are talking about. So we apply 2 times a normation step. But here the normation step in the tuple space, you know, this is irrelevant. If I would have summed up all those norms here, for example, I would also got a norm which is equivalent to this norm, because the small L1 norm is equivalent to the small L2 norm in a finite dimensional tuple space. That is what is behind that. So try to prove that. So this means it does not matter so much what we are doing here, how we take these norms of the derivatives and make some norm out of that, but it's helpful to take the same procedure, that is then in the WKP spaces where you do not take the Euclidean norm then in the tuple space, we take the small LP norm. So we take the numbers, put them to the power p, sum them up, and take the pth root out of that. Okay, this is one remark. And the other remark is from time to time it is helpful to introduce these quantities, which only have one bar here. So we have the 2 bars and the k for the full hk norm. And here for an index L between 0 and k, we introduce this quantity. So we do the same thing, but we only consider the derivatives of order L, not of order less or equal L, but of order L. And we know if we exclude the special case L equal to 0, this only gives, in a general situation, this only gives a semi-norm and not a norm. If we only have the derivatives and have no further information about the function, we only can conclude that the derivative is 0 and not that the function is 0. And on the other hand, as it's written here, the full norm is then built up of all those semi-norms going through all the orders. And this is all consistent with the notation we had up till now. So what we had up till now was the H1 norm, so up to the first derivative. We had introduced also the scalar product with a 0 order part, the L2 part, and the part concerning the first order derivatives. And this, in a little bit more compact, we can write with the gradients and with the Euclidean scalar product here of the gradients. But that's the same thing. Okay, so we have more or less argumented now that what we have introduced here with these bilinear forms are scalar products on the Sobolev spaces hk of omega, and that is that the k norms we have introduced are really norms on this space. And now comes the important property that we are now correct with this definition of the spaces, namely those spaces are complete with these norms, they are Hilbert spaces. I will sketch very briefly the proof. It's quite simple. So what do we have to do? We start with a Cauchy sequence in HK, and we have to find an element in HK towards which this sequence converges with respect to this norm. That is the notion of completeness. So having a Cauchy sequence in HK means that all derivatives, look again at the definition of the norms, that all derivatives are Cauchy sequences in L2. The L2 space is complete. This is the knowledge we now use. This is something which has to be proved before, which is not, I don't feel responsible for proving that. That is analysis, function analysis, whatever. Okay, so the L2 is complete. Therefore, all these sequences, the function sequence, the first derivative sequence of all first derivatives, of all second derivatives, and so on, they all converge to individual functions. So what is the missing thing which we still have to prove? So we have something like, so we start off with, say, a sequence UN being a Cauchy sequence. Okay, I write German at the blackboard, then CF. Cauchy sequence in HK of omega, and therefore we know that all derivatives of this sequence are Cauchy sequences in L2 for all derivatives of order less or equal to, should take here a multi-index here, of less or equal to k. And therefore, by this completeness, there exists, let's say, something like U alpha from L2 such that this sequence converges to U alpha in L2. So what do I have to know now that everything is okay? What do I have to know about those functions here? How can I find? So what is a candidate for my limit? What is the candidate for my limit? How shall I choose this? It's here contained here. What is the? Yeah, what about this here? Take the limit of the function itself in L2. But at the moment, it's still only the function, it's only a limit in L2, not in HK. So we not only need that the function sequence converges, but we also need that all the derivatives converge. Converge to what? Yeah, so what does that mean? We need to know that this here is the corresponding derivative of u. If this would be the case, then this would just say, okay, I have a function. This function is the limit in L2 of the function sequence, and that all their derivatives are the limit of the corresponding derivative sequences, and that means in the notion of the HK norm, there is convergence in the HK norm. How can I see this, that this is really the case here? What kind of results you know if you think in classical terms, in pointwise derivatives? So what would that mean? We have a function sequence which converges in some sense. We know the function sequence, we have derivative sequences. So it's, of course, we have the derivative sequence, they also converge. And then we want to know, we do only one step, that the limit is also differentiable and has as the limit and is the limit of the differential of the derivative sequence. In which situation you can justify that? What do you know from analysis about that? When can you guarantee this? Give me some sufficient condition. Okay, I repeat it again. So I have the following situation. You have a sequence of functions which converge. Let's do it in one variable. I know that the derivative converges to something. And now I want to know that u is differentiable and that the derivative of u is v. That is the same question now both for one derivative. So what would be sufficient here? So in which norm? Give me a norm. What would you suggest? We are now talking first about pointwise derivative, everything classical. So what do you know from analysis where you have this notion of? Okay, let me say, I give you an assertion. My assertion is if I have pointwise convergence here, I have pointwise convergence here, and then this holds true. Who agrees with me? Who disagrees with me? Unfortunately, there are no jokers here in this game. You are on your own. All the jokers are already spent. Yeah, this obviously does not work, cannot work. In the classical setting, you need uniform convergence in both cases. So you need quite strong convergence. The amazing thing with the weak derivatives is what I claim here. For the weak derivatives, also L2 convergence is good. And why is this so? Okay, what means a derivative? What is a weak derivative? It was this situation. So we have here the weak derivative, whatever, And what kind of function has this to be? It has to be the function which in this testing with the test function phi from the test space, it must be the one which fulfills this identity where all the derivatives are over to the test function, epsilon. So that is the notion of weak derivative. Now we have a sequence. Okay. Now we need, what we would like to have here, we would like to have convergence now. And correspondingly, we would like to have convergence here. And if we can justify this, then we can say, okay, and then this limit element, let's make it a little bit neutral, then this limit element is the weak derivative of u. That is what stands here. So the only thing I have to do is I have to justify these two convergence steps of numbers here. We are talking here about numbers. So what is this? This sequence is convergence to this guy in L2. This is a smooth function, an L2 function. So this whole thing is convergence, just the L2 scalar product here. The same thing here. And you see, I need much, much, much less than the L2 convergence. I need just convergence in this sense. Convergence in this sense of testing with something and then the sequence of numbers converge. That's what's called weak convergence. So I only need this notion of weak convergence as it stands here, such that I can exchange limit and derivative. That is what I want to do. So to make a long story short, the space is complete. Okay, and now we have to see a few more properties. This is a very simple property. So one thing which is quite important to work with these spaces is to relate them to each other. To relate means to find out which of the space is a subset of the others, but we want to have more. We want not to have the embedding, we want to have a continuous embedding. That is, if we, for example, what does that mean? For example, the assertion is, and that is a very simple assertion, if I have the hk and the hl, and the k is bigger than the l, I have more derivatives here, then first of all, this is a smaller space. Okay? I think this is clear. But also this embedding is continuous in the sense, if I take now the identity map, or from here to here, then this is a continuous map. That is, I can estimate the norm, the higher norm here. I can estimate the norm in the bigger space here, the lower norm here, by the higher norm. And also this is quite elementary. I can estimate the L norm by the K norm, but because in the K norm there are more derivatives involved. It's just some additional terms. So this is the first of the possible continuous embeddings to work with. This is a very trivial one. If I have an H2 function, of course I have an H1 function. If I have it better, I have it also in the not so good. And this is a little bit more involved estimate, only first written up in H1, in one-dimensional. We saw already an example showing us that in 2 dimension and from 2 dimension on, the functions in H1 need not to be bounded. In particular, they're not continuous functions. We had this specific example with the logarithm, which has a weak singularity, but nevertheless is an H1 function. In this theorem tells us, in 1 dimension, this is better. In so far that the H1 of AB, so these are those functions which are L2 functions, and the first weak derivatives are also L2 functions. They are necessarily continuous functions. What does that mean? We said we always have to deal with equivalence classes of functions. So that means if this function is not continuous, it was just we were not really able to write the function down properly. So there may be a few points. A few means up to a set of measure 0, where we have defined the function in a non-proper way, such that maybe it was not continuous there. But these discontinuities are removable, and if we do so, then we end up with a continuous function. And one can also do a little bit better. And this is not only a set relation, it's a continuous embedding. That is, I can estimate the norm of such an H1 function. The norm is now the norm of the image space, so the infinity norm, the maximum norm. I can estimate the maximum norm by a constant times the 1 norm. Of course, I cannot do that if I would have a 0 here. I cannot estimate the maximum norm by the L2 norm, but the assertion is in 1D, I can estimate the maximum norm by taking into account the L2 norm of the function plus the L2 norm of the derivative, of the weak derivative. Okay, so now we have to deal a little bit with this problem, how to define Dirichlet boundary conditions, taking into account that the boundary of a domain in the sense of the d-dimensional Lebesgue measure is a set of measures 0. So this does not make sense to say that an L2 function is supposed to be 0 at the boundary in the sense of the d-dimensional Lebesgue measure. So it would be no problem if the functions would be continuous functions, but unfortunately they are not, up to this special case of one space dimension. So in one space dimension there's no problem. In one space dimension we can really say what is the function at the two endpoints of the interval, but in more than one dimension it's a little bit more problematic. And here again is this example I mentioned, which shows us this is a function which is not continuous, but nevertheless in 2 dimensions here on the disk it is still in H1. Okay, so the answer to this problem is we want to speak about the boundary of the domain. If we look at the boundary in the d-dimensional Lebesgue measure, this doesn't make sense. It's of measure 0. So we have to have, so to speak, a d minus 1 dimensional Lebesgue measure on the boundary. This requires a certain smoothness of the boundary. We could do that, for example, if we would have a half space. It's not a bounded domain, so it does not really fit into our theory, but let's say we have a half space. So we in RD, and we consider those points where, say, x1, the first coordinate, is greater to 0. Then the boundary would be just then the d minus 1 dimensional space with the components x2 to xd. So we would have a Lebesgue measure there, and things were okay. And this, what we see there globally in this case, we have now to do locally. So locally, our boundary has to look like a flat plane, or at least a smooth hypersurface. Smooth in the sense describable as the level set of a function, as typically the 0 set of a function. And the smoothness of the functions we can use, this defines then the smoothness of the domain. So what we would like to have is that locally in a boundary point, we can choose a coordinate system such that in relation to this coordinate system, the hypersurface, this maybe is a little bit misleading, this is meant in a nonlinear setting. So it can be then understood with respect to this coordinate system as a hypersurface, and this means as the set of zeros of some function f in these local coordinates. How is this? For example, if this is on our domain here, so how shall I do this with this domain? Which coordinate systems I should use? So how many do I need here? Okay, if we can do this for every point, a set, if we're talking about a compact set, we can restrict ourselves to finitely many, which overlap then each other, and so on. Guess you know this from analysis. So in this case, how many coordinate systems do I need? To represent the boundary in terms as the zero set of a function of a certain smoothness. Yeah, give me the coordinates. Why, so I have a global coordinate system. Maybe I can also work with a global coordinate system. Maybe I haven't. Okay, we first try this coordinate system. We do not change anything. So what would be now the functional representation of the boundary?
Function of theta or the angle?
Yeah, now we have said, okay, we do not change anything. So x and y. Can I express this here in x and y as a function, say, of x? Let's say of x now. For example, this part of the boundary. Can I do so? Is this part of a boundary a function of x? I guess so. Pretty smooth function. C infinity. Why? So what are the points? The points here are x squared plus y squared equals to 1. So what is this? We have y squared equals 1 minus x squared square root of that. That is my function, or that is my function f. And if I said I want to have it as a set of zeros, this is my function. Okay, this is my. Maybe I was a little bit unclear with the zero set. I really want to write. I correct myself. I really want to write one of the components in terms of the remaining d minus 1 components. And here I did this. This is my f of x. This is a smooth function. And I can do this a little bit larger, and then here I get problems. That means I need another local representation. I need here at least 2. But nevertheless, my functions are C infinity functions, and therefore I call this domain then a C infinity domain. So depending on the smoothness of those functions with which I can locally, now I really have to say it again because with this, I understand that you were confused. It was not 100% precise what I said. I want locally to describe my surface as a function of d minus 1 variables, and the d's variable is then the functional value, as we have seen here. And the smoothness of the functions I could choose here, this determines the smoothness of the domain. So if I can do this only with Lipschitz continuous functions, I call the domain a Lipschitz domain. If I can do it with CK function, a CK domain, and with C infinity function, C infinity domain. And in this sense, this is a C infinity domain here. So, okay, this does not really work totally. I could, so I get problems in these 2 points here. I can only represent the part here and the part here. And then I have to take one further coordinate system to get an overlapping situation where I also include these 2 points. What about this example here? C infinity, CK, Lipschitz, nothing. Everything is piecewise here. As you say, Lipschitz. Why not C1? These corners here make problems. Okay, if you only look at these parts, of course, this could do this very nicely, but this makes problem. Here we would, for example, choose this coordinate system. And then we see we have a Lipschitz function, but of course not a C1 function. Okay. So Lipschitz will be the minimal requirement, what we are doing. So we allow for corners. And there's a further requirement, and this is written down here. We have to be able to choose these local coordinate systems such that we can represent the boundary as hypersurfaces, as explained. And we always want to have that the domain is on one side. What does that mean? That the domain is on one side. So locally, I have here a situation where I say y equals f of x. And locally, I want to have that locally the domain, not the whole domain, but the domain in the vicinity of in a vicinity of this boundary. What would then be the characteristics here? That would be then y is less or equal than f of x, or maybe or greater or equal than f of x, but not both. This means locally on one side. And now we come to this example here. So we take a circle and we slit it here. It could be a very simple crack model, for example. Mechanically meant, of course. Okay, so you see, with the representation of the boundary, it's not a big problem. That's a Lipschitz boundary. But we have no chance to get the domain concerning this boundary. The domain is not locally on one side here. So this is an example we have to exclude. This is too irregular that we can treat it. Okay, so in the following we have a Lipschitz domain. And as I said already, due to the compactness of the boundary of the delta omega, it's sufficient to work with finitely many of these mappings of these coordinate systems. And on the basis of this finite sequence of mappings, we can introduce a measure, a d-dimensional measure. On the basis of this measure, which corresponds then to the Lebesgue measure in the full d-1 dimensional case. It's sometimes also called the Hausdorff measure. And in this sense, we can also speak of L2 functions on the boundary. So that means, basically, it means we can stretch locally the boundary to some full d-dimensional, or to a part of a d-1 dimensional space, and then we do as till now. Okay, so we will also now deal with the L2 space on the boundary, and not only the L2 space, we will also have correspondingly, I think we avoid it to a large extent, but of course you can also think of Sobolev spaces. Then of course you have to define derivatives in local coordinates on these hypersurfaces. So we have to do analysis on manifolds. I try to avoid this to some extent. Okay, so now what does this help us in conjunction with this question? What about now, how can we, what is a proper notion for saying an H1 function, a non-continuous H1 function is 0 at the boundary? And for that we look at this space here. This is a pretty smooth space. So this is now our standard situation, a bounded Lipschitz domain, and we consider those functions on this bounded domain which can be prolongated. V can be prolongated to a function V tilde, and this function V tilde is a C infinity function on the whole domain. So, or you can also see it otherwise. The functions we are looking at are the restrictions of all C infinity functions on the full space to this domain. And by this restriction, so to speak, we do not see the domain anymore. And also we do not see the irregularities of the boundary. That also means that we have to need some basic requirements for the boundary to do so, and it turns out to be this bounded domain. So with this very smooth function, we now can describe, in some sense, the H1 functions. And so far, now the next statement, which I'm not going to prove, which is quite technical to prove, is this space of smooth functions is dense in H1. That means for each H1 function, which is a very strange function, maybe, I can find a sequence of very smooth functions, namely from this category, such that in the H1 norm this sequence converges to the functions I really want to consider. And this will now be typical. We will find spaces of smooth functions which are dense in the Sobolev spaces. And that means we can work, in principle we can work nearly all the time with smooth functions. And then in the end something comes out. And the only thing which we have to see then, that this what comes out then has to be compatible with this limit process. And then we also have it for the general functions. I will explain this in a second. So because we have this now, and we have this next building stone, namely for these very smooth functions, of course we can define what is the function restricted to the boundary. This we can do. Well, continuous functions is now a C infinity function, so this is well defined, this thing here. So the first assertion is what comes out here is also an L2 function on the boundary. And the second assertion is this embedding, or it's not an embedding, this restriction. This one also it calls this here then the trace of the function at the boundary. This is a continuous, first of all, it's of course a linear operation. If I take the trace of a sum, it's a sum of the traces. And it's also a continuous operation. That means I can estimate the L2 norm of the trace here for these very smooth functions by the H1 norm of these smooth functions. And now I can use the density. The density now gives me the possibility to extend this trace operator, which is concrete for this small space of very smooth functions. I can extend in a unique fashion this trace operator to the full H1, giving me a trace for every H1 function by a continuous and linear mapping. How would I do this in general? Of course, I would say, so I want to define this mapping for a larger set. So what I would do, I would say I would first take my general H1 function, and I would approximate it by a sequence of smooth functions. As this sequence of smooth function is converging, also the limit sequence is converging to something that is the continuity of the mapping, and this something is now the candidate to be the image on the extended operator here. And the only thing which I have to make clear is, that is a minor technical point, is if I take different sequences to approximate the element I'm looking at, of course in the end I have to end up with the same trace in the end. This is the only thing one has to think about. So what we have it by this way, we have a linear and continuous mapping attributing to each H1 function a trace in L2. The continuity is encoded here in this estimate, saying the L2 norm of the trace can be estimated by a constant times the H1 norm of this H1 function. Okay. This mapping is not surjective, so that we do not cover, the image space is not the full L2 space. It's a strictly smaller space, it's a closed space, so it's again a complete space. And as it is closed, of course, we also have no charge, we have nothing like density as we had before. So that means not every L2 function can appear as a trace. And this is of importance later on for dealing with non-homogeneous boundary conditions. When we say we have a boundary value problem and we have some function which should be the boundary conditions we would like to impose. then the minimal requirement, of course, is that there is an H1 function which has this boundary function as the trace. We do not want to have just a function, we want to have a solution of the PDE and so on. But if there's not, if it's impossible that such a function exists, of course, there cannot be a solution for the PDE. So this is then a necessary requirement for this boundary condition, and this is something stronger than just saying the function is in L2. This space also has a name. This is the H1 half. So there are those functions which are 1/2 times differentiable. Okay. Let's just take it as a name. We will also not really use it or need it. Okay. So, but going back to the very smooth function, the trace is what we expect to be the trace of just the function at the boundary. Yeah, and now we can say we can deal with at least with homogeneous Dirichlet boundary conditions, where we have seen we should incorporate the boundary condition in the space, and we had the problems at least in the new definition of the space how to denote that, how to say that the function is 0 at the boundary. Now we know how to do that, so we look at those H1 functions with a property that their trace function as an L2 function on the boundary is just a 0 function. And this, as we had it already, this gets the new name H1 0. And this is now also a closed subspace of the H1 space, because it's just the pre-image of a continuous operator of a bounded set, so of a closed set, so it must be closed. And by this, as it is closed, it's also a complete space. So this is a strictly smaller Sobolev space than the Sobolev space H1 of omega. Okay. For the H1 of omega, we had seen that those functions which are so smooth that they don't see the boundary in some sense, they are dense in this space. For the H1 0, we can work with a subset of that, namely with the test functions which we know already, which are C infinity functions with compact support. Because this reflects a situation that we sort of stay away from the boundary with the support. Not really in the H1 0 function, but in its smooth approximation. So now let me indicate a little bit how one can work with these density properties. For example, we have, in deriving the weak formulation, we have seen we need something like partial integration. That was very essential there. So we need formulas for partial integration for hopefully quite general situations. And there is such a formula for partial integration. So that's just the formula for partial integration, saying I consider one of the derivatives, the ith derivative. I can bring the ith derivatives over to the other factor in the integrand. And in addition, I get a boundary integral over the product terms in the direction of the new ith component. So that would be the basic partial integration formula in d dimensions which we would like to see. So the first thing, of course, is we need something like a normal field. So we need a vector field at the boundary of length 1 pointing orthogonally to the outside. And that is the first part of the assertion I'm not going to prove. Under the assumption of a bounded Lipschitz domain, this unit outer normal, die äußere Einheitsnormale, exists almost everywhere at the boundary and gives an L infinity function then. Or each component gives an L infinity function, or it's a vector valued L infinity function. So what is the statement here saying it's an L infinity function? what is the point in noting that that's an L infinity function? Because if I take it's the unit normal, it has Euclidean length 1. So can I just erase that, or is there some further information hidden here? What does it mean to be an L infinity function? There are two properties actually involved, namely yeah. Okay, the second condition, that's exactly the point. And the second condition we, so to speak, we have encoded in the notion, the boundedness. It's not only essentially bounded, it's really bounded. But the measurability, that is what is stated here. It's not only a pointwise definition of the normal, but the function which we get has some basic property as a function in the sense that it's at least a measurable function. And because it's a measurable function, it can appear in integrals, and we can work with it in integrals. Okay. Of course, it's clear that these normal cannot exist everywhere, isn't it? There are some exceptional points which are unavoidable. You see the exceptional points here, where the normal does not exist? That's a Lipschitz domain, we said. Nevertheless, there are some exceptional points, a set of measures 0 where it does not exist. Okay, so how could we prove this? We could prove this thing here classically. Okay, we need to have that the derivatives exist and so on, and then we need also the functions at the boundary, and then hopefully we are able to prove that. But how can we extend then this result now to the general situation as it is asserted here? Here it is asserted that it also holds true if the v and the w are just h1 functions. And so to speak, the only thing what we have to do is we have to check whether that the thing which comes out makes sense for h1 functions or not. Of course, if there's something is required which an h1 function cannot provide, then it cannot make sense. If we would require that the fifth derivative is bounded, that an h1 function cannot provide. But that's what we'd like to have. We have here the first derivative, so that's an L2 function. Here we have an L2 function, so this integral is well defined. The same applies here. And what about now these two things here? This is the trace of an h1 function. This makes sense and is an L2 on the boundary. Correspondingly here. So I have here on the boundary L2, L2, and L infinity. And this integral is again well defined, because just take the integral in the modulus, you can estimate the third factor by a constant, the L infinity, and the rest is Cauchy-Schwarz. So all these terms make sense, and this is more or less already a justification that it also holds true. That, of course, what we have to do, we have to approximate those functions with correspondingly smooth functions, and that can be pretty smooth functions, C infinity on the whole domain, where in any case this formula is valid. So we get this formula everywhere with an n here, and then we have to go to the limit. But because all these quantities which we have here converge in L2, because the sequence converges in H1, so the functions itself converges, but also their derivatives converge in L2. All these things here converge correspondingly here. Here also, here we have to take into account the continuity of the trace operator. And then in the end, we get the same thing, the same formula in the limit. Okay, so having this as a basic formula for h1 function, now we can build up on this. Cannot complete it today, but let's do maybe one or two further steps. For example, if I know more about my function, for example, if I know it's an h2 function. If an h2 function means all my derivatives are h1 functions. So all my derivatives applying the trace theorem have traces. So now I also, in this situation, I not only have traces of the function, I also have traces of the derivatives. Having traces of the derivatives means I can also form this linear combination with the outer unit normal here, which is then again an L2 function. So I can the outer normal, the normal derivative of the function on the boundary is well defined and is an L2 function. So for an H2 function, I have an extended trace operator, which does not only give me the function values as a trace, but also in an extended version, the normal derivative. So this gives me a possibility for a explicit formulation of something like Neumann or mixed boundary conditions, if necessary. And here's the argument again why this is so. As I said, if I have an H2 function, then I go continuously to the derivatives as H1 functions. I go continuously to the traces, and then I go continuously to the product with the L infinity component, and that's it. Okay, the next step is to put the things together. So if we have this thing here, where is it? Let's go back. If I have this thing here, and I put it together for all the components, then I have a term like this here. If I always take the same other partner, now if I add up all the equations, I get then here the scalar product. The QIs, let's compare again. The QIs correspond to the W, and the derivatives of the V are now the components of the gradient of V. So I get this part, I get this part, and I get this part, just by summing up the corresponding equations. So this is now the partial integration formula we have used it. And maybe as the last thing, we are not yet complete, but as the last thing, if we now know more, if we now know have a W in H1, but V in H2, then we said the gradient of V is in H1 component-wise, each component of the gradient of V in H1. So the gradient of V is now allowed to play the role of the Q here. That means I get here the Q is my gradient of V. Here I have now divergence of gradient of V. This is Laplacian of V. And correspondingly, I have here now partial derivatives times the normal vector, that is the normal derivative of V. So that would be, so to speak, the formula which tells us directly, I start here with a Laplacian, this is my weak formulation part, and in the general situation, which we until now have excluded by having our boundary conditions, there is this boundary term.